Okay, we've spent some time talking about different types of signals or functions, but the title of the course is actually Signals and Systems. So let's turn our attention now to a discussion of systems. So this is a fairly general term. Will include all of our electrical circuits, but it also applies to mechanical systems. In this particular course, we are going to concentrate on systems that have a single input that often we just call X of t, and then these systems perform some transformation on the input. We'll call the transformation S. Sometimes I'll call this T as well, but somehow does a transformation on the input S to produce a transformed signal at the output of the system that we can denote as S of X of t. Often I'll call this just Y of t, would be the output of the system. So in this course we'll concentrate on systems with a single input and a single output. In more advanced courses you may deal with more complex systems that have multiple inputs and even multiple outputs. So again, just a brief recap of the notation. Y of t is the output of our system when the input is X of t. Sometimes I'll simplify the notation and drop the dependence on t just to make the notation a little simpler, but Y of t and X of t will always be functions of time in this course. And in many cases S represents a differential equation relationship between the output and the input X. That's certainly true for our circuits. Now let's turn to different system classifications. This is in section 1.7 of your textbook. System classification. And in particular in this course we'll be concerned primarily with linear time invariant systems, but we need to be able to differentiate a linear system from a nonlinear system, and we'll also talk about time invariance, and we'll talk about other classifications as well. So a linear system, notationally we can write this as if Y1 is our system output when the input is X1, and Y2 is the system output with input X2. The system is linear if when we apply a scaled version of X1, K1 X1, so K1 here is just a constant, so this would represent just an amplification or an attenuation of input, just a change in the amplitude. But we apply a scaled version of X1 plus a scaled version of X2 to the input of our system. If that produces a scaled version of Y1 plus the scale version of Y2. Okay. Now this is one definition, or definition of linearity, or a check for linearity. It involves just this one comparison between what do we get when we apply this is input to the scaled versions of Y1 and Y2. I find it usually simpler though, instead of using this one equation, to actually do two separate checks for linearity. So again, if we define y1 to be the output of our system when the input is x1, and y2 to be the output when the system is x2. A system is linear if, when we apply a scaled version of x1, so k1 x1, we get a scaled version of y1. Okay, and so this check for linearity has two checks or comparisons, and when we apply as the input to our system the sum x1 plus x2, and that produces the sum y1 plus y2, then both of these checks, if a system satisfies both of these conditions, then it's also linear. So although there are two checks we have to apply, as opposed to on the previous slide where there was only a single check, these checks are a little simpler to apply in practice. Now, for a system to be linear, both these comparisons have to hold. If either one fails, then the system is non-linear. Okay. Now, we've looked at the equations. Let me show you in block diagram form what these two equations represent. So the first equation, where we're comparing ky1 to I'll call it k1 x1. We apply k1y1 to the output when we apply a scaled input. Remember, to find y1, we just apply x1 as an input, and then we multiply that by k1. So to get the left-hand side of this equation, what that represents is, we have, in block diagram form, we have x1 coming into our system, okay, S. That produces y1. Okay. We amplify that or attenuate that, and this means just multiply it by a constant k1. Then the output of this block diagram would be k1y1. Now, what the right-hand side represents or says is that now if we amplify k1 with x1 as input, this would produce as output here k1 x1, and then now we apply this to the system. This produces, the input to our system is now k1 x1, so the output is now the transformation applied to k1 x1. What we want to do is compare these two. Okay. So if these are equal, and this is the first step in our check for linearity. If they're equal, then it's past this condition to be a linear system. Okay, and essentially, looking at the block diagram, it essentially says that one condition for linearity is we can swap the system transformation and just a linear scaling or amplification of the signal. And if we do that and we get the same result, then at least we've passed this condition for linearity. Okay. The second condition requires that y1 plus y2 is the same as what we get when we apply the sum of these two signals. So again, what the left-hand side represents here, again with x1 coming into our system, we know that produces, this is what our notation represents, that produces y1. And then with x2 coming into an identical system, does the same system transformation, that produces y2. Then we sum these two. Okay. this then produces y1 plus y2. So this is what the left-hand side of this condition represents. On the right-hand side, we actually, what it says to do is we have x1 and x2. We sum these. Okay. That would produce x1 plus x2. And then now we run this into that same system, S. Then the output of this system is the transformation applied to that sum. Okay. So now here, to pass this condition for linearity, we want to compare these two signals. Okay. And if they're identical, then the system is a linear system. So again, it's got to pass both conditions, the scaling condition as well as this summation condition, or this additive property. This additive property says that we can swap this summation and the system transformation. And I'll show you an example of this a little later on how to check for linearity. The block diagrams help a little bit, but this is one of the more confusing topics in this chapter. These being able to classify these different systems. Just a couple of notes. It is true that all linear constant coefficient differential equations are linear. You can prove that, but in general that's true. Again, if you have a linear constant coefficient differential equation, not all differential equations are linear, of course, but if it's a linear constant coefficient differential equation, then that describes a system that is also linear. And then something else that we'll run into later on is that the total response of a linear system, due to this additive property, can be broken down into two parts. A sum of a zero input part, that's the output that depends only on the system state, only on like initial voltages on capacitors or initial currents through inductors. And then we add to that the zero state response. That's the part of the response that depends only on the input, doesn't depend on any initial conditions. The output in general then, the total response can be shown to be the sum of those two. Okay. One more thing I want to show in this video, in this portion of the video, is how to distinguish between a time invariant system, which I'll often abbreviate TI, okay, versus a time varying system. And in this course, we will focus on linear time invariant systems. So again, given input X to our system, that produces output Y. Actually, let me scratch that. I want to go back to my more complex notation of showing the time dependence here on both the input and the output. So if our system has input X and that produces output Y, then a system is time invariant if we apply a time delayed version of the input. Here I'm going to show it shifted to the right by capital T seconds. If that produces, if that's identical to the result I get by time delaying the output when the input is X of T. So this is the check for time invariance. Okay. notationally, or in block diagram form, the way we can represent this is with x of t coming in. I know that goes into my system. That produces y of t. Okay. And then now if I delay y of t by t seconds, I'll represent that just by a block. Then this is y of t minus t. Okay. Now this is actually a block diagram representation of the left side of this equation. For the right side, I have x of t as input. I have my delay element first. So the output of my delay element is a delayed version of x of t. Now I apply that to my system. Okay. So what this produces, now this is not y of t, or even y of t minus t. Okay, I'm not quite sure. Y of t is what I get when I have x of t coming into my system. You know, I'm not guaranteed in general that with x of t minus t that I'm going to get y of t minus t out. That's not true for all systems. So with this input, what I know I do get out is a delayed version. I have the delay of x of t, and then my system does this transformation. So now I have to compare these two. Okay. And if I find that a delayed version of the output is equal to the output I get when I apply a delayed version of the input, then the system is time invariant. Okay. I know these are pretty confusing concepts. I'll work through a couple of example problems in an additional video. I'm going to conclude this video, and then in the next video we'll talk about some other system comparisons.